Good afternoon, guys. So we will start today. Today we are going to start with the NMR spectroscopy. Let me recap the things what we did in the last lecture. We are covered UV and IR spectroscopy, UV visible and IR spectroscopy, which is basically required for getting some information about the structure, but not the complete structural elucidation. Whereas the each spectroscopy give a specific information about the structure of the organic molecules. Like UV spectroscopy deals with the chromophore oxychrome present in the molecules, or is there any conjugations with the chromophore? That information is not sufficient, so we go for the IR, which is directly deals with the structural functional groups. The organic molecules will have specific active molecules that is we called as a functional group, which gives that IR spectroscopy directly gives the information about the functional group. But in connections with the rest of the molecules or the group of molecules or group of atoms together, where they join exactly, what is the pattern of joining, that information you won't get it through IR or UV. So there is another very important technique in spectroscopy that is we called as NMR spectroscopy. So it is also called as PMR and CMR, that is related to the nuclear proton and carbon. So in this talk, we are going to talk about the PMR and CMR, that is proton magnetic resonance and carbon magnetic resonance. In combined, we called this technique as a nuclear magnetic resonance spectroscopy. Now, this is a spectroscopy technique. That means we're going to use a light as a source for the getting some informations from the molecules. That is we call as interaction of light with the matter. Now, in contrast to the electromagnetic spectrum, the very least energetic source, that is radio wave frequency, will be used in studying the NMR spectroscopy technique. Now, if you see, this technique is studying a couple of nuclei, which is having a unique property like a spin of the nuclei. You know, the spin of the nuclei is based on the composition of the their nucleons, whether there is a odd mass or odd number of nucleons. So based on that, there is a fermions and bosons. We should be proud that this name boson is originated with the honor to the Satyendranath Bose, the Indian scientist. Okay, the nuclei which is having a spin 1, that is even mass nuclei with the odd number of proton, or it may be the E1. So such types of nuclei are not NMR active, but the nuclei which are active, these are the half integral spin, like take the example of proton C13, fluorine 19, P31. So these four nuclei are most widely used in spectroscopy technique to study the organic molecules. So what exactly the NMR spectroscopy? Now this spectroscopy technique is there in MSc part 1 as well as in part 2. But if you see the theoretical aspect, in same 3 we have studied the NMR spectroscopy with the detailed technique like cozy head core. But here in contrast to the practical aspect, we need to know proton NMR and C13 NMR and DEPT as well. In case of those who are studying TY-BSc, we have the proton NMR in detail. So they will also get benefit out of this talk, as well as the part 1 and part 2. So all three uh, the category students will definitely benefit out of this lecture. So what is exactly the nuclear magnetic resonance? That is we call as NMR spectroscopy. As I told you, the nuclei which is having a half integral spin, I is equal to half, they consider to be a bar magnet when they spin at their own axis. When such nuclei having I is equal to half, like proton C13, fluorine 19, phosphorus 31, when they spin at their own axis at certain RPM, they produces magnetic field. That is we call as induced magnetic field. When such induced magnetic field, when remain as an individual entity, it move in a random directions. If you see the diagram over here, you can easily understand what does it mean. If you see here, this diagram, first diagram deals with the movement of the the nucleon at their own axis, that is spinning of the nuclei. When they spin, it produces a small magnetic field, which is range in terms of energy is 0.1 to uh, 0.1 calorie, which is exactly matches in terms of the radio frequency in calorie particularly. So that magnetic field, it responds to the energy we are talking about in terms of the energy levels. So when such nuclei are without any field, when they are together, they are moving randomly, and they do not have any directions, because you know the magnetic field will have two directions, north and south. Now you know there are two effects normally we do study in particular physics or physical chemistry, that when the small magnetic field, when placed in a strong electronic field or magnetic field, there is a loss of degeneracy. Now here in the second diagram, all the nuclei are having the same energy levels, or we can say the same environment. We don't know which one is high and which one is low in terms of their magnetic field. So when they place in a strong magnetic field, that is we call as the applied magnetic field, B0, what will happen? Most of the nuclei which are having a similar type of magnetic field, like north side or south side, they themselves arrange. When they arrange themselves with the magnetic field, that is we call that alignment with the magnetic field. So these are the low energetic transition. Like take the example of these nuclei will place in a ground state, that is a lower energetic state, that is we call as a plus half. Those nuclei which are opposed to the applied magnetic field, they will place in a higher energy state, that is we called as minus half, that will have certainly higher energy than the plus half one. So in the second diagram, you cannot understand which nuclei which is having a higher energy or lower energy. But when they place in a strong magnetic field, according to the Zeeman effect, the degeneration of this nuclei will lose, and definitely they will themselves arrange into the two field. What are those two field? Plus half and minus half. If you see the second diagram over here, I will let you know the second diagram. Now, as I told you, when the nuclei spin at their own axis. Like take this one example, this nuclei spinning, it produces certain magnetic field, north, south, south, north. So suppose there is a north, south that is being called as a plus half nuclei, that is alpha nuclei, which are aligned with the magnetic field. So this is the alignment with the applied magnetic field. This is applied magnetic field. So these nuclei are placed with a lower energy state. And another one is the red one. They are against the applied magnetic field. That means their magnetic field is exactly opposite. So this energy gap, particularly now you can say the plus half and minus half have certain amount of energy, and that amount of energy plays, in as I mentioned in the earlier slide, there is a kilocalorie or calorie energy in terms of the energy, this energy levels particularly. So that is directly related to the applied magnetic field. So this energy, which is in between the plus half and minus half, it is directly proportional to what? The applied magnetic field. So as you increase the applied magnetic field, the gap between this plus half and minus half goes on increasing, and that have different applications that we will see later. But in the beginning, you understand when the spinning nuclei placed in a strong magnetic field, they themselves arrange with the field and against the field. So it will have two fields, the lower energy field that is aligned with the magnetic field, and against the applied magnetic field that is a higher energy. So that means when there is a energy levels, the lower energy levels and the higher energy levels, certainly we need to do the transformations over here from plus half to the minus half. And that terminology over in case of NMR spectroscopy is called as flipping of the proton, or flipping of the nuclear from ground state to the excited state. That is the lower energy state to the higher energy state. So this energy gap particularly is matches with what? The energy from radio waves. So that amount of energy which is found in radio waves, that exactly matches with this quantum, particularly the photons, which we are talking about to transit this plus half into the minus half, is exactly matches with the radio frequency. That's why we do select the radio frequency as a source in proton magnetic resonance. So here, the light we use, that's why this is a spectroscopy technique. With the help of light, we are going to identify something that means structural information about the molecule. So this is what we call as a spectroscopy. So with the help of light, we are getting some information. Now come to the three words, that NMR, the nuclear which is having a half spin when placed in a strong magnetic field. That means M. The nuclei which spin at their own axis produces a magnetic field. When placed in a strong magnet, as per the Zeeman effect, they show the plus half and minus half, that energy level splitting, that is we called as a loss of degeneracy. And when we put the radio frequency source as an energy to do the flipping, that is we call it the transitions, that energy, that radio frequency energy particularly, is matches with this energy gap, and there is a flipping of the plus half into the minus half. That when it will happen, when the energy gap of this will matches to the radio frequency energy, that we call as a resonance. So this energy gap, the energy levels having certain energy which will matches with the radio frequency, and that amount of energy will do the flipping, that is a plus half into the minus half, and that is we call as a resonance. So the three words is related to the nuclear, which is specific nuclei which is having a half integral spin, magnetic field, induced magnetic field interact with the applied magnetic field, and there is a alignment with the nuclei with the field and against the field, and then there is a resonance. So these three words are related to the nuclear magnetic resonance. Now let's see in detail about this technique. Now look at here, there are certain nuclei which is used here in this NMR spectroscopy, that particularly the proton. So we have here proton, which gyromagnetic ratio is roughly 40, and abundance, natural abundance is almost 100%. If you just compare with the carbon, the gyromagnetic ratio is considered to be 10, and their percentage, that natural abundance is 1%. Just that four things you just remember. Abundance is 100% for the hydrogen. That means it is plenty of H1 found in the compound, that is a organic molecules. Whereas C13 is 1% only. So the sensitivity of the molecule, sensitivity of the instrument depends upon the nuclei, which is in abundant quantity. Now, proton is in abundance, so proton NMR is considered to be more sensitive than the C13 NMR because C13 is 1% only in the organic molecules. When we study, most of the organic molecules contain carbon, which is C12, which is 99%, where 1% is C13. So the sensitivity of the instrument will be less in terms of the this abundance. Another important thing now, the gyromagnetic ratio is directly related to the magnetic field required for the resonance. So in case of proton magnetic resonance, suppose we have 400 megahertz as a instrument, that means we are going to use equivalent amount of magnetic field, 400. So if that is a radio frequency also 400 megahertz, and that much equivalent of magnetic field will be required. So if you go from proton NMR to the C13, so the applied magnetic field required for this will be less 4 times than the proton. So if it is 400, this will be 100. So that is a basic difference in terms of the instrument. Most of the cases, the instruments names are given as per the radio frequency source used, and which is directly proportional to the magnetic field. So more the in terms of the proton NMR, the magnetic field required will be more, and in case of C13, there is a less magnetic field required because of their gyromagnetic field. So this type of questions, most of the cases ask in NET set examination. So you should remember this. Now, this is a basic instrument where, again, I will just briefly understand what exactly this. So this is NMR tube here. The glass NMR tube is there. Sample will be filled with the deuterated solvent, and sample required from 5 milligram to 50 milligram depends upon the instrumental frequency. This is a radio frequency source. This is an applied magnetic field, a strong applied magnetic field. And what will happen? There is a coil. This coil will spin this NMR tube with certain RPM. When the tube spin at certain RPM, the inside solvent containing compound, no doubt having a proton, having a carbon, having a proton or fluorine or phosphorus, that depends which technique you are looking for. So if such nuclei are there in the sample, when it spin at certain RPM, each nuclei particularly acts as a bar magnet. Suppose you are focusing on proton. So the proton is considered to be a bar magnet. It produces magnetic field. When they place in a strong magnet, what will happen? The degeneracy will lose, and there will be two energy levels, plus half and minus half. And then we place a radio frequency source on the sample. And then what will happen? There is a flipping from plus half to the minus half, and certain nuclei, particularly proton nuclei, having a different groups like maybe CS3, CS2, OH, or NH2. Wherever you will find the proton, they will absorb the radio frequency, and certain radio frequency signals will be given as an output, and that will be computed in the form of the signals. And see, this is the exact schematic diagram of the NMR spectrum. If you see here in this diagram, this is a dome where the supermagnet is there. This is a place over here. We have to insert the NMR tube. This is a robotic thing. So here, the NMR tube will be inserted here. And this is completely a robotic machine. This is considered to be a dome with a super magnet. The NMR tube will go inside, it will be spin, and the radio frequency will be bombarded across this, and then it will give you some signals in terms of the spectrum. So this is what exactly the how NMR spectrum looks, how NMR spectrophotometer looks. Now look at here inside. As I told you, this is how the supermagnets will be placed, because there should be a liquid nitrogen helium mixture, and NMR tube will be placed over here, and it will spin at certain RPM. And obviously the supermagnet will produce a certain magnetic field required for the flipping, and then everything will be as such as we have discussed. This is another application of NMR spectroscopy, that is MRI, or the CT scan, which is used for scanning the human body of certain structural or medicinal problems, particularly in terms of some disorders. Now, what are the exact application of NMR spectroscopy? This is the most important part actually required for the structural elucidation. Now, what informations you will drawn from the NMR spectrum? The first and very important information is number of signals. Now, what is number of signals? Number of signals gives the exact information about how many different types of hydrogens are there in the molecules. Like take the example, there is a CH3, CH2, CH, or maybe OH or NH2 or carbon. Wherever there is a hydrogen atom having a different group, so that type of different groups gives you the signals in the NMR spectrum. If are having 5 signals in the spectrum, that means 5 different types of hydrogens are present in the molecules. That clear information you will get in terms of the number of signals. Now, this number of signals also related to the positions where exactly they are lying in the NMR spectrum from the standard. So standard is considered to be a TMS. From TMS, how far it is going, whether it is going to the deshielding zone or towards the zero. Towards the zero, we call as shielded one. Away from the zero, we call as a deshielded one. So the position of the signals we call as a chemical shift, which is measured in Del. Del is the unit for NMR spectrometry values over here. And that is measured in terms of Del, that is a parts per million as unit of this Del. We will see that in a minute, how exactly it is calculated and what exactly this chemical shift. So the what type of hydrogens are there? Now we have got here some 5 signals, but what type of, whether they are deshielded or shielded, where their chemical shift value is low or high. So that can be easily studied with the help of the position of the signals. Third one, the relative area under the study. That means if suppose we have the peak over here, how much is the area under this peak? That means what if suppose some of the peaks are short, some of the peaks are tall. So that height of the signal, that is we call as integral height, gives you the exact value about the quantitative measures of the hydrogen, how many hydrogens are there, whether there are 3 hydrogens, where there are 6 hydrogens, where there are 9 hydrogens. That quantitative measures will be easily understand with the help of relative area under the signals. So how far, how long that signal is. The fourth and most important informations you will run from the NMR spectrum is splitting pattern. Now, from the splitting pattern, now in case of the low resolution spectra, you will get the signal. Signals means the single line spectrum. But if you see the high resolution, that splitting will occur, and exactly you will get the information about the neighboring group. So if we have a CS3 group, the CS3 group, if it is like a triplet, that means it is nearby the 2 protons. If it is a quartet, it is nearby the 3 protons, and if it is a doublet, if it is singlet, you will get the information about 1 or no proton. So that type of information can be easily drawn with the help of the splitting pattern. So we'll move on to the next. Now look at here, first application, that is the number of signals. Now suppose we have the protons, different protons will be there in the molecules. Like take the example, protons not as a single entity, it will be the group of proton. So the CS3 is a group of proton, that is the 3 protons together, but this all 3 protons will be same. This 3 protons will be same. Okay, just a minute. So these 3 protons will be same, and these 3 protons will be same. The important thing is what if there is a symmetry between these 2 protons, that means if the environment is same, then this proton as well as this proton will have a similar environment. There will be a single line for the same line for this and same line for this and the same position. So the height of the signals will be very high, because it will be a 6 proton signals. If there is a 2 different protons like CS3 and CS2, these 2 different protons are there. So there will be 2 signals, one signal for this, another signal for this. So the height of this proton will be a little bit higher than this, because this is related to the 3 proton, this is related to the 2 protons. Now, if you see here this example, that ethyl, methyl ether. Now this CS3 and this CS3 is not same, because this CS3 is attached to the O, this CS3 attached to the CH2. So wherever you find that CH3, CH2, CH, or any group which is having slightly different to their attachment, they all will show the signals in the NMR spectrum. So this technique is so sensitive. So slight difference in the environment will show the different signals, and that different signals will give the crucial information about the structural information about the molecules. Now look at the structure like cyclo propane, the cyclopropane with it, which is monosubstituted. Now here, in terms of the uh, condensed structure over here, we'll know that this proton is over here, these two protons are here, these two protons are there. And we will understand that this 1, 2, 3 signals may be there. But it is not like that. We have to study their this type of structure, that the above two protons are close to the Cl. So these two are same. This is directly attached to this, and these two protons are away from this. So there are the three signals because of one for this, another for these two, another for these two. So three peaks will be like this, but not like that. This peak or this peak or this peak. Understand? So like this, if we are talking about the condensed form of this vinyl chloride, we may confuse if it is given like CH2Cl, we may say this is one proton and two protons. But if you see the geometrical structure, that this Cl is close to this H. So this proton is different. This is cis, this is trans. So these two protons are completely different, and this is geminal to this. So that is directly attached to the carbon, same carbon. So all three protons, this one, and this one will be different, and you will end up with the three peaks instead of two peaks like this, one or two. So always draw the geometrical structure to avoid the confusion if there is a double bond. Now suppose we have here this structure dichloroethane. Now here this dichloromethane have a symmetry that this CH2 and this CH2 is having a same environment because it is C attached to the Cl and this is attached to the Cl. So obviously this both the proton will have a same environment. So this both the CH2 will give the one signal only, and the height of the peak will be high. Obviously this two proton plus two protons, so four proton peak will be there. Whereas in case of this chlorobromo compound, where this CH2 and this CH2 is completely different because the electronegativity of this is different and the middle one will be different. So 1, 2, 3 peaks will be get. Now if you see the methyl acetate, so this methyl group is attached to the O and this methyl group is attached to the carbonyl group. So the electronic environment about the CH3 is completely different, and that's why you will get the two signals for this. Now ethanol, obviously this one, and this one, all three groups of protons are different. So you will end up with the three signals. Move on to the next. Now already we have discussed about this. I just wanted to skip this one. Okay. Now look at the below one. This particular example, already we have discussed this too. Now, this one is, this CH3 is different than this CH. So obviously you will get 1, 2 peaks. Now here, in this molecules, you will get the two signals. Why it is so? Because there is a symmetry. If you put a plane over here, this CH3 and this CH3 is same. This H and this H is same. So if there is a plane of symmetry, you will see the half of the peak. The half of the peak will exactly overlap on the each other, because you will get the 6 proton one single line and 2 proton one single line. Now here, this is again the same as like a vinyl chloride, vinyl bromide, 1, 2, 3. Now if you see here benzene ring, all 6 protons are same, so you will get the single line. If there is a monosubstituted aromatic ring, obviously the ortho protons, these two will be same. The meta protons, obviously they will be same, and this para one to the NO2 will be different. So 1, 2, and 3. 3 signals you will get in case of a monosubstituted aromatic ring, apart from any substitute across this. So this 2 protons are same, these 2 protons are same, and this one is different. Okay. So move on to the next. Look at here, this example. 1, 2, 3. So 3 signals you will get. This CH3 and this CH3 will be same because they are joined to the CH, which is having a Br. So you will get 2 signals. Here you will get 3 signals. Obviously, this 3 will be there. This will be 1 signal. And here this is methyl and tertiary butyl ether. So this tertiary butyl, that means CH3, CH3, and this CH3. So the 9 protons will be having same environment. So 9 proton will have 1 peak and the 1 peak for the CH3. So 2 signals you will get. Now look at here this example, paradise substituted pattern. Now this is a nitrobenzene No doubt there is a symmetry over here. So this proton and this proton is same. Obviously, this one and this one is same. So you will get single line. If the symmetry has been lost with the bromide, then this two proton will be same and this two proton will be same. But this one and this one is different. So you will get one peak for this and two peaks for this. Meta will obviously have, this is a different, this will be different, this will be different, and this will be different. So 1, 2, 3, and 4. 4 signals you will get for this. Now for dinitro, meta dinitrobenzene, we'll have a symmetry, no doubt. So this one and this one is same. This one is different, and no doubt this one is different. So 1, 2, and 3. So 3 signals you will get for this. Now here there is a complete symmetry. So this one and this one is same, this one and this one is same. So 2 signals you will get. Whereas in case of bromo derivative of nitrobenzene, this one and this one is there, is different, this one is different, this one is there. So total peaks will be 4 for this. Move on to the next. Now, how the spectrum looks in terms of the NMR spectroscopy. The spectrum look like this, where the standard will be at the extreme right hand side of the spectrum. This is a standard. From this standard, we are going to measure the difference between this standard and this peak observed. So this is we call as a chemical shift, no doubt. The distance between the TMS and the peak observed is called as chemical shift, which is measured in del, which unit is parts per million. Now, if you see here, the actual scale of the NMR spectroscopy is in hertz, because we are going to use a hertz as a frequency because we are using a light. But if you use here, suppose 100 megahertz instrument, 300 megahertz instrument, 400 megahertz instrument, or 500 megahertz instrument, each time the scale would have been changed. And then every time the instrument has been changed and their readings will be changed. So it would be a mess. So it has been converted into the del, and which is a simple ratio of del is nothing but the ratio of peak observed in hertz into the instrumental frequency, that is in megahertz, into 10 to the power 6. So this is a simple unit. I will just show you in a minute. Now, what is chemical shift? Chemical shift is what? Observed chemical shift in hertz. Like suppose we have here scale 300, 600, instrument is 300 megahertz. So your scale started with 300, 600, 900, and so on. Now, this is a observed frequency like 300, 600, 900. So which will be measured in hertz. Instrumental frequency, we refer this instrumental frequency, that magnetic field, and the radio frequency source, which will be directly proportional. That means megahertz is considered to be instrumental frequency over here. So megahertz, that is 300 megahertz. So 300 into 10 to the power 6. And we need to convert this del into the parts per million. So we have to multiply this into 10 to the power 6. So if we multiply with the 10 to the power 6, what will happen? This unit will be parts per million. So parts per million is the unit. Suppose if you want to understand this, I will just show you what exactly this. Del is what? Observed frequency. Observed frequency will be, suppose 300 is the megahertz. 300 megahertz is the instrumental frequency. And 300, 400, 300, 600 hertz will be the scale actual. So this is in hertz. Instrumental frequency is 300 megahertz, that means 10 to the power 6. And we have to convert del into the parts per million. So this will be converted into multiply by 10 to the power 6. Now, if it is like this, then 10 to the power 6 will cancel. This will get cancelled. So 300 hertz means 1 del. So this will be the straightaway equation. Now, if you look at this, what I said in this diagram, 300 is considered to be a 1, 600 considered to be a 1. Like straight away 300 divided by 300, that will be 1. 600 divided by 300, 2, 9, 3, and so on. So if you see 100 megahertz as an instrument, then what will be the scale over here? It will be 100, 200, 300, and so on. So the 100 upon 100, it will be again 1. 200 upon 100, it will be 2. So this way, the scale will be fixed apart from the instrumental frequency. Whether the instrument is 600 or 700 or 1000, your del scale will be constant throughout. So this is the simple calculations. Now we will see some problems based on this. Now look at here. What it says, the chemical, this del units is constant regardless of the operational frequency. That is the instrumental frequency. If it is 100 or maybe the 500, it will be constant. So it does not change the chemical shift value. So example is, now any nuclei which is having a 2 del as a stretching, sorry, is a frequency, NMR frequency, which is recorded at 60 megahertz. Now, if I change the instrument to the 300 megahertz, will that del will change? The peak will remain constant, because I said this is constant for this del value is constant for this instrumental frequency. Whether it is 700 or 600, your del value will not change, because it's a ratio. Why it is a ratio? Because the thing is that if you see the formula is observed frequency upon instrumental frequency in hertz, like 1000, suppose 100 upon 100. So that will be like a, you can say the 1. So like that, 300 upon 300, this is what the 1. So if the 300 is the instrumental frequency and 300 will be the scale in hertz, so 300 upon 300 will be the 1. If it is like 400, obviously 400 upon 400 will be 1. So apart from the instrumental frequency, the del will be a constant value throughout. So let's see another example. Now, what exactly the use? Why do we need to use the change in the instrumental frequency, like from 300 maybe to 600 or maybe the 800 or 900? If you see here, this two scale, 300 is bit compressed structure, whereas 600 is going to be a little bit well separate, because of the more room for the peak to appear in a nice way. So in simple, if you use a magnetic field more, that means instrumental frequency will be more, and ultimately the resolution of the spectrum will be better. So more than instrumental frequency, more better resolutions you will get. Like if we have a 1600 megahertz instrument also, but their peak which will appear, they will be very concentrated, that they will be appeared in the second order, they will compact together. But if you use a higher frequency, obviously there will be a better resolution and you can easily read out the spectra. Now look at here some of the problems with the constant frequency, instrumental frequency. Now this is acetone, which is recorded at 200 megahertz as a frequency, instrumental frequency. So that gives you the CS3 peak at 2.1 del. Now the question is, how many hertz downfield from the TMS does the acetone resonance corresponds to? Iska matlab kya ho raha hai? The meaning is very simple. The whatever del value we have given over here, 2.1, with the instrumental frequency 200 megahertz, they have asked the convert this del into the hertz. So del into the hertz, your hertz is the observed frequency. Del is the converted frequency, and instrumental frequency is 200. So del is equal to observed frequency upon instrumental frequency. Suppose you have a del, instrumental frequency will be directly into, you will get the hertz. So 2.1 into 200 will get directly hertz. So that is 2.1 into 200, that will be the your hertz. What another question they are asked, if the H1 NMR spectrum of acetone were recorded at 500 megahertz frequency, what would be the position of the absorptions in del? So as already we have discussed, if the instrumental frequency has been changed from 200 to 500, there will be no change in the del value, because it's a constant. So it will be no doubt 2.1. So this value will be 2.1 into 200. That number will be in hertz. So this is what the value. Now C questions. How many hertz downfield from TMS does the 500 spectrum? That means you have to convert that this 2.1 del into hertz. So again, 2.1 into 500, that will be the hertz from the 0 to downfield. That is what we converted the actual scale of the NMR spectrum. So this hertz is the actual scale. This is what the actual scale of the NMR spectrum. So what is that? This is the actual scale. Let's move on to the next. Now look at here, another very simple questions. Now, this type of questions will be asked in the next set examinations, and which is very simple once you understand. Now, what is the problem? The problem is the following spectrum. Okay, the following H1 peak was recorded to be the 200 megahertz and convert this into Dell units. Now, this is all are in hertz. Okay, hertz frequency. Now, you want to convert this into Dell. What you are going to do, simply divide by 200. That will give you exactly the Dell unit, because you know the Dell is what? Hertz upon instrumental frequency. So this is the instrumental frequency. So you want a Del is equal to the observed frequency. This is the observed frequencies. So observed frequency upon the instrumental frequency. So this divide by 200, that will give you something 7 point something. So this will be 3 point something. And this will be like, again, you can just calculate and you will understand the what exactly the Del value. So this is how to solve such types of problem. Now, what is TMS? TMS is the standard used in proton or C-theory, or in particular NMR spectroscopy. Now, what are the beauty of this TMS? TMS is having a 12 proton, which are having an exactly same environment. It is soluble in the almost all organic solvents. It shows the sharp singlet at extreme end of the NMR spectrum, which is right side of the NMR spectrum. And because of the electropositivity of the silicon, most of the organic carbon containing compounds or hydrogen containing or oxygen, nitrogen, halogen, they almost are more electronegative than the silicon, and they go away from the zero, that is a TMS, that is from the standard. So that's why this TMS is considered to be a zero, is said to be a zero and considered to be a reference in NMR spectroscopy. And it is non-toxic, easily removable just by giving some heat treatment, and easy to handle. So that's why we prefer to use as a TMS as a standard. In the olden time, we used to use as a carbon tetrachloride as a standard, but because of the toxic nature, we don't use now carbon tetrachloride. Now look at here, this is a spectrum. Now this spectrum here at the extreme right-hand side over here, this is what your TMS, which we consider as a zero. Now, if your peaks are towards zero, that is we called as upfield. And if the peaks are going away from the zero, that is we call as downfield. Downfield means, now understand what exactly the meaning of this. Downfield, that is also called as a deshielded, and this is we call as shielded. Now, when the peaks are observed away from the zero, that is we called as a downfield. That means the required magnetic field for the resonance will be less. Now, if you see the simple mathematical equations, what is that? If you see here, del is what? This is a ratio, that applied magnetic field. This is the applied magnetic field. We have converted into the instrumental frequency. So if the denominator required is less, so obviously del will be more. So the required frequency, which is directly proportional to the magnetic field. So what I said the magnetic field. That means when the nuclei spin at their own axis, placed in a strong magnet, and they align with the magnetic field. So most of the nuclei, when they align with the magnetic field, that means the required energy for the flip will be less. You understand? Like take the example, you are going in a, you are like riding a cycle and you are going in the same direction where there is a wind. So you will require less amount of energy to paddle. Exactly opposite situation, if you are riding a cycle and the wind is in opposite direction, you have to paddle with the more energy. In the same fashion, you can see here this upfield and downfield. Now, if your peak is towards the zero, that means the required frequency for the flipping will be more. That means the denominator will be more. That means their del value will be, denominator will be more. That means the del value will be less. If the denominator is less, what will be the case in case of the, I said denominator is more. That means applied magnetic field required will be more. If it is more, your peak will be going towards the zero. That means your peak is close to zero. That means maybe 9.9 or 1. So that is highly shielded one. Like if it is an electronic environment, if it is in the electronic environment, like electron withdrawing group, then what will happen? Because of the less shielding of the electron, they produces the magnetic field in a such a fashion, they produces a same magnetic field which is reinforcing to the applied magnetic field. That means the applied magnetic field required will be less. That means the instrumental frequency required is less. That means denominator will be less. Ultimately, the del value will be more. So the peak will have higher del value. So this is the shielding and deshielding phenomena. So let me comment on the shielding and deshielding phenomena in brief to understand, because this is very much important to understand this concept. Now look at here. Suppose this is a nuclei, proton nuclei. Okay, so let me just take the another. Just give me another. Okay, now look at here. This is the nuclei, proton nuclei. Now this proton nuclei is around the electron. Okay, so this is the new electronic environment. And another condition, there is a nuclei. Okay, and there are some same electron, but here this is attached with any electron withdrawing group. What will happen? Now this is attached to the CH3. Now CH3s don't have any effect to withdraw the electron, whereas in case of electron withdrawing group, they withdraw the electron. So what will happen in case of the electron withdrawing group? So the shielded electrons, so electrons around this proton will be less. Okay, so in case of the this case, there are more electron around this proton, which produces magnetic field, which is exactly opposite in directions. Opposite in direction, that means the required magnetic field will be more, and the required magnetic field will be more. That means this denominator will be high, and ultimately this will be, if this is high, this will be low. You understand? If the required magnetic field will be high, so this will be low. So this is highly shielded because of the electron. Now, if there is an electron withdrawing group, the electron withdrawing group pull the electron, and the less number of electrons will be around this nuclei, that is a proton, which is under study. So the nuclei which is there, they are produce magnetic field which is in the same direction to this applied magnetic field. So the required magnetic field will be less. So if the denominator is less, ultimately this del value will be high. So this proton is considered to be deshielded. These protons are considered to be shielded. Shielded means required frequency will be high, required frequency will be less. So this is the simple meaning of. So let's move on to the next. Now, what are the factors which affect the chemical shift values? Now, these chemical shift values differ by different factors. The first one is shielding and deshielding. Just now we have discussed. If there is any electron withdrawing group around the nuclei which is under study, no doubt the required magnetic field or frequency will be less. So ultimately, they are having a higher del value. So such types of nuclei are called as deshielded nuclei or deshielding or shielding phenomena. Hybridization. Let's take the example of S characters: sp2 hybridized, sp3 hybridized, sp hybridized will have a different S character. More the S character, less will be the electronegativity or the attraction of the electron towards the nucleus. So S character in case of acetylenic, that is a triple bond containing compound, will be 50%. So most of the most of these triple bond containing compound like acetylenic compound, they are more acidic as compared to the sp2 and sp3 hybridization. So this is one thing. So the electronegativity is directly related to the S character, but this will have a reverse effect we will see in a minute. Third one is magnetic anisotropy. So this is the anomaly behavior of the nuclear. Normally we know that more the electronegativity, the shielding will be more. But here there is a supporting thing towards the applied magnetic field. That means any effect which induces the applied magnetic field in the same direction to the applied magnetic field. Okay, So that induction in the magnetic field will consider to be a anisotropy, and which is caused by a pi electron around the nuclei which is under study. Like take the example of aldehyde. Now aldehyde is attached to the carbonyl group. Come on, what is that? Someone mute, mute karo thora. Okay, so we'll see this magnetic anisotropy in a minute. And there is another example, another factor, that is hydrogen bonding. So these four factors are there which affect the chemical shift value, that is a del value. The del value will change because of these four factors. Now let's see one by one. So first is electronegativity. If you see, the more the electronegativity, more will the del value. Like take the example of fluoro, then chlorobromo. The electronegativity goes on changing. So as the electronegativity change, the chemical shift value also change. Now this is another example, the hybridizations, as we said. This first line is considered to be a sp3 hybridized, this one. The del value is ranging in the range of 0.8 to 1.7. This is sp2 hybridized, but we are talking about sp3 group. Okay, so this is allelic proton. So roughly these are the shielded one. Whereas we consider this olefinic one, that is a double bond. So this double bond, that is a vinylic protons, are 4.6 to roughly 6, that is 5.7. This is higher del value. Whereas the carbonyl group, which is having H, this del value is considered to be 9.5 to 10. So this aldehyde proton, which is sp2 hybridized, this is also sp2 hybridized, this is also sp2 hybridized, will have very high effect on chemical shift value. Whereas triple bond, this del value is considered to be 2 to 2.3. If you consider this is sp2 hybridized and this is sp hybridized, so this sp2 hybridized is less electronegative, whereas sp hybridized compound is considered to be more electronegative. So acetylenic protons are more acidic than the olefinic. But whereas the effect in terms of the chemical shift is reverse. So there are certain factors in terms of the acetylenic compound, because the structure is linear, and whereas the structure of the sp2 hybridized is trigonal planar. So because of this, there is only one structure, and because of the only one structure, the induction in magnetic field, that is we called as the magnetic field, which is produced by this sp2 hybridized proton, are in the same direction to the applied magnetic field. So the applied magnetic field required will be less. That means the frequency required for the flipping will be less. And ultimately, if the magnetic field, the denominator required is less, obviously the del value will be more. Whereas in case of acetylene, there are two structures. One is linear, another one is your horizontal. And because of that, one structure is reinforced, another one is opposing. So the net results is less because of these two structures of acetylene, because of their linear structure. So there are the two structures, the linear and vertical. So obviously horizontal, linear. So one structure reinforced, another one opposed, and ultimately the effect is less. Whereas in case of olefinic proton, there will be only one structure, so there is a reinforcement only. So in case of this acetylenic, there is a opposing field. So this is the reason. That's why this del value, that is acetylenic del value, is considered to be lower than the olefinic, apart from their electronegativity. So this is a chart. I don't want to go through this chart. You all know. Now another is the integral height of the signals. As I mentioned in the first slide, where that height of the peak is directly related to the quantitative measures of the number of protons. Now here there are 9 protons. Here there are 3 protons. The height of the peak is like 60 millimeter, and this is 20 millimeter. So the millimeter height is directly related to the number of protons. Now, how it will be like studied? That there is a standard in the NMR spectrum. We have to fix one standard, and as with the standard, we can take the integral height of the another peaks in the software particularly. So this is a operational thing. So that nothing to do over here, but you just understand integral height is directly related to the number of proton. Now the another most important part, or I forgot here one application, that is hydrogen bonding. So hydrogen bonding in terms of the olefinic proton, if you see here OH peak is roughly in the range of 1 to 5. Okay, so this OH peak. But here, if there are some OH peak which are in hydrogen bonding concept, like take the example of salicylaldehyde. Now salicylaldehyde having OH group which is in intramolecular hydrogen bonding, where in case of the OH peak, which is normally 1 to 5 or 6, in case of the salicylaldehyde, the OH peak will be in the range of 14 del, 14 ppm. So because of the hydrogen bonding, the chemical shift is hugely affected. So next application is what? Splitting pattern, that is spin-spin coupling. Now what is this spin-spin coupling? The spin-spin coupling is giving you the exact information about the neighboring group of the proton. Now if you are targeting that one of the nuclei which is under study, what are the nearby nuclei to that which influence the nuclei which is under study? So that exact information you will get it from this spin-spin coupling, that is we call as first order equation, that is n plus 1. That n plus 1 is derived from the spin quantum number, that is, you know, that 2i plus 1. Now we know that I is equal to half is the condition for the NMR spectrum. Those nuclei which is having a half integral spin, they are only studied in case of NMR spectrum. So if I place here I value, so it will be like this. So this 2 will get cancelled, will left only n plus 1. So the n plus 1 is the standard equation of the first order equations in terms of the splitting pattern or spin-spin coupling, where n is considered to be a neighboring group of proton or neighboring nuclei which will couple with the nuclei which is under study. Now we'll understand what exactly it will be applicable in terms of NMR spectroscopy, how it will be useful. Now this is the simple NMR spectrum, where this is your compound called as 1,2,2,2 tribromoethane. Now this compound will have two nuclei, which is CH2 and CH. Now the CH2 is influenced by the CH and CH is influenced by CH2. So if I see the peak of CH2, which is doublet, and this is a first peak, because of the electronegativity, there is a attachment of one bromide. So the less electronegative element, which will have 4 ppm, roughly 4 ppm, which appear to be a doublet because of the CH which is in neighboring. So according to the n plus 1, so if I targeted CH2, the neighboring group is CH. So n plus 1, n is equal to CH. So CH means 1 proton, and 1 plus 1 means 2. So 2 lines you will get. Now, if I target the CH, which is close to the 2 bromide, so that means higher del value. So which is nearby 2 protons. 2 protons means 2 plus 1, 3. So 3 lines spectrum you will get, that is a triplet. 3 line spectrum is called as a triplet, and this looks like this. Suppose we have here now ethyl bromide. So the ethyl bromide structure is CH2, CH3. Now here, this CH3 is close to the CH2. That means CH3 will give the triplet 3-line spectrum, and CH will give the 4-line spectrum because this is near to the 3 protons, so it will give the quartet. So triplet quartet pattern is fixed for the ethyl type of groups. Let's move to the next. Now, how this triplet, quartet, singlet, doublet is originated? That is originated because of the spin-spin coupling. Now, what is the spin-spin coupling? You understand? It's very simple. Now, take the example of first type. This first type, that is 2 protons are there, HA and HB. Now, suppose This HA is nearby HB, that means with the one protons only. That means if I study this HA, which is close to the HB, that is one proton, so the closed proton is having one spin. So the one spin of the proton can be clockwise or can be anti-clockwise. So if there is a one proton near to the proton which is under study, can be written two way, the clockwise or half anti-clockwise. That means the plus half and minus half. Now suppose this is the HA under study, which is having a two nuclei around it. So this two nuclear spin, maybe both will be clockwise or both may be the anti-clockwise, and there is a mixture, one clockwise, anti-clockwise and clockwise, anti-clockwise, anti-clockwise, clockwise. So this is a mix maximum combination of the spin, which is uh, there is no any fourth outcomes. So this is the maximum combination of this spin. So as many combinations are possible, that times that peak will have intensity. Like here, this is one time, this is one time, and this is two times combination. So the intensity of this will be 1:2, 2:1. So here there is a 1:1 possibility. So 1:1 is the intensity of that peak. Now this HA, we're talking about only HA. Now this HA is nearby three nuclei. So the three nuclei spin will be, all three will be clockwise, all three will be anti-clockwise, and there is a mix combinations, and that mix combinations only three times like this and three times like this. So how to remember this? First, you can make two clockwise, another one anti-clockwise, another mix one, another one is anti and two clockwise. And exactly in the second way, so this will be your clockwise and two anti-clockwise and so on. So maximum combinations will be like 1:2, 3:2, 3:1. So maximum combination means the height of the peak, the maximum spin, that means the maximum the height of that particular peak, that is the intensity of that peak. So 1:2, 3:2, 3:1 is considered to be Pascal intensity of this particular HA. If it is nearby three proton, if it is nearby two proton, if it is nearby one proton. So one proton will give the doublet, two proton give the triplet, three proton give the quartet, but that is because of this spin combination. That's why it is called as spin multiplicity or splitting. So this is because of the spin combination. Now another important informations about the splitted peak is the coupling constant, which is constant throughout. It is not related to any type of hurdles, like if the instrumental frequency is changed, it does not affect at all the coupling constant, which will be measured in hertz. Now, why it is measured in hertz? If you know, the original scale of the NMR spectrum is considered to be a hertz, that is observed frequency. Now, when we have a peak, like take the example, I will show you the spectrum. Just a minute. Now, this is a spectrum, original spectrum. Now, the original scale is hertz, like 100, 200, 300, and 400. Now, if you see the splitted peak like A, the distance between the splitted peak is nothing but the J. Now, I will show you here. Now, this is a doublet. If you see here, HA is nearby one proton. This is B. So, HAB will show the doublet. So, this is a doublet. So, this distance is J. Now, this J is in hertz, because if you plot the extra plot across the instrumental spectrum, you will see this is the scale is hertz. So this is nothing but the spacing distance of the splitted peak as a J. Now, if you have the middle one peak, now middle one peak will correspond to the two different types of proton, HA and HC. So first it will split into the doublet. So this is a doublet. Now look, one thing that HA couples with HB, reverse is HB couples with HA. So when HA couples with HB and HB couples with HA, both will have a same J value. So this J value for this will be exactly same. Now, when the HB couples with HC, it may have a different coupling constant. So if the coupling constant is lower than the A, obviously you will see the 3-line spectrum because of this 2 proton. So this is a doublet of triplet. This is called as doublet of triplet. First, it will show you the doublet, and then doublet will split into the triplet, and this triplet twice will be seen in the spectrum. Now, HC is nearby only 1 proton. So this will give you the doublet. Now, when the HB couples with HB couples with HC, this spacing distance is this, that is less than this. So when reverse HC couples with HB, the distance will be same. Like, look, this distance and this distance is same. Now, if I experimentally show you that this J value is 6, okay, this value is 6. So this value will be again 6. This 6, and suppose this is 3, then it will be 3. That is 3 hertz. So that means what exactly informations you are getting from this coupling constant? If the coupling constants are matching with some other coupling constant, that means that 2 groups are same, they are joined together. Now look here, this HA and HB coupling constant is matching, this one and this one. So that means this couples with this and this couples with this. Now this HC and HB matching with this, that means this joined with this and this joined with this. So that coupling constant gives the exact information about the group which is coupled to which one. So that is what we call as a coupling constant, and that gives you the exact information about the joining of the different groups of the atoms or groups of the molecules particularly which are active in NMR. Now look at here, there are certain fixed values for this. Coupling constants are considered to be one of the tools to identify certain structure in the molecules. Like coupling constant is very high, like 11 to 18 hertz. 11 to 18 hertz in the spectrum, that you can easily come to the conclusion that this double bond having proton, they are transient positions. If the coupling constant is lower than 10, like 5 to 10, so obviously that considered to be a cis type of coupling. And if the coupling constant is very, very low, like 0 to 3, then it may be geminal type of proton. So this is vicinal, geminal, and these are the trans proton. So each one have a fixed value. Now look at here, this C is splitted as a doublet of doublet. Now how? This C will couple with this B as a cis coupling, and this is a trans. Now this will be considered as a doublet of doublet. So this is a doublet of doublet. Now this HA will couple with this, and this HC will couple. So that means this will also give you the doublet of doublet, and this is also doublet of doublet. So all these peaks is considered to be a doublet of doublet. Okay, so this is a doublet of doublet, but how we get confused with the quartet and doublet? Now look at here. If we have a peak like this is with the Pascal intensity 1:3, 3:1 we have seen. How this is 1:3, 3:1 because of the spin-spin coupling. Whereas the Pascal intensity for the doublet of doublet, obviously it will be 1:1. So 1:1, 1:1, 1:1. So the intensity for the doublet of doublet will be completely different. Their appearance will also different. So this appearance will be different. This appearance will be different. Most of the cases we do get confused. So always you have to see their appearance. Now look at here this example. CS3, CS2, CS2, Br. Now this CS, the terminal A, that is couples with this B. So this will be triplet. The terminal one attached to the Br will again be the triplet. Now, if you see the middle one is next to the CH3 and CH2. That means it will give the quartet first, and then that quartet will split it into the triplet, 3 line. So this is a quartet of triplet. That means it will give the first 4 line, and each 4 line will split it further into the 3 lines. Now, the coupling constant plays a vital role here to show the appearance of the peak splitted in actual spectrum. Now look at here. If the coupling constant of one of the proton is very, very less, okay, then what will happen? four lines, that is a quartet. First, this CH2 will couple with the CH3, so you'll get a quartet, that is the four line. So this is your J. So this value will be same for all. So what I said this coupling constant is very high as compared to when this couples into this CH2. So CH2 will have, suppose this is like a 10 and this is like a 3. So if the coupling constant of one of the proton which is coupled is very, very less like this, then what will happen? This will show you exactly the lines which are expected, like 3, like here, this gives you the 4 line and this gives a 3 line. 3 into 4, that means 12 line spectrum. So the 12 line spectrum will be this, subjected that if the coupling constant is hugely differ, if the coupling constant is hugely differ, then what will happen? The exact multiplet will be in terms of the hyperfine splitting, that 4 into 3, that is a 12 lines. But in case of some of the peaks, if the coupling constant is higher in number, like take the example over here, this, when this couples with this and this, like if this value is 10 hertz and this is 5 hertz, some of the lines will merge, like this line and these lines for this will overlap. So these 3 lines will merge out of this. So out of this 12, 3 lines when merged, you will get in appearance on the spectrum 9 lines multiplied. Another thing, if the coupling constant is now same, equal, like 10 as to 10, 10 for this and 10 for this, then what will happen? The half of the lines will overlap and you will have only 6 line, and that 6 line will be as per the first order n plus 1 equation, whereas this 9 line and 12 line is considered to be a second order spectrum. Their appearance will be absolutely different, whereas the n plus 1 rule will be exactly applicable over here. Now look at here, this middle CH2, nearby 3 proton, this side 2 proton, this side 3 plus 2, 5, 5 plus 1, 6, 6 line. So this will exactly obey the n plus 1 equations and give you the 6 line spectrum. So this is considered to be absolutely first order n plus equation to have a clear splitted peak as a multiplet, which will be considered to be 6 line as a multiplet. Now Pascal has given some of the pattern, like if there is a 1 proton nearby, then we call it as a singlet, and then doublet, then triplet, quartet, pentet, sextet, heptet, and so on, and their Pascal frequency, which is because of the n plus 1 rule. You all know this. Now look at here some of the spectrum, how they look. Now look at here. This is a proton NMR of alcohol, where this alcohol is very much mutuous in terms of their del value, because always the OH proton is exchanged with the impurity, so their value will lie from 1 to 5 up to 6. Whereas the CH2 and CH3, obviously the CH2 field will give the quartet because of the 3 protons, so this will be upfield, this will be downfield, and the CH3 will be upfield towards the 0. So this is the spectrum of ethanol. Look at here the spectrum of something like propionic acid. Now here, this is the acidic peak, which is 10 point something or 11, 12. Okay. Now here, this is a quartet for this and doublet for this. So this is the quartet for this 1 proton, which is nearby 3 proton, and 3 proton is nearby 1 proton. So this is a doublet. And this 3J is a 3 bond coupling. That means this proton and this proton couple, that in between there are 3 bond, 1, 2, 3. So that's why it is called as 3J. Normal coupling is 3J. Now look at here. This is nitro compound, nitropropane. Now here, this is going to be, now look at here. This is triplet for this. This is sextet. This is triplet. Look at here, 2 nitropropane. This will be doublet for this because it is nearby, only 1 proton. Then this will be a multiplet because it will be a septet, that is 7 line spectrum. This is a doublet again. Now this is all about the proton NMR. So I think today we will stop over here, and tomorrow we'll talk about the CMR and mass spectrum, and thereafter tomorrow we will take the exact spectrum for the analysis. So with this, we will stop here with this, and then the tomorrow link will be posted. So with this, thank you. See you tomorrow. Bye.